In this first lesson for Chapter 7, we're going to introduce you to probability distributions. And this particular chapter focuses on these distributions for discrete variables, not for continuous variables. That'll be our next unit of, and final unit of study actually for the course. So just a couple quick reviews about probability and about discrete versus continuous variables. So probability we just learned about in our previous unit. And probability distributions are specifically graphs of probability of a certain event happening versus the value of that event. Okay, we call this the random variable, and we're going to look at different types of distributions where the random variable is a different type of thing. We want to remember that all probabilities for a given experiment or for a given scenario always add up to a value of 1 if you're working with probabilities that are in decimal form, or they all add up to 100 if you're working with probabilities that are in percentages. In terms of discrete and continuous, again, discrete variables are those that we get by counting things, not from measuring things. So they have very discrete, defined values. They can't be decimal representations, only derived from counting. So let's get into an example of how we can look at discrete variable probability distributions. We're going to begin by rolling 2 dice, and we're going to let the sum of the 2 dice be the random variable x. To clarify a little bit of notation, the random variable x is written as a capital letter, just in defining what it is, but capital letter X can have a whole bunch of individual values, which we refer to as little x. So slight differences in notation. Not difficult. Okay. So I've drawn off to the side here a chart that we've become very familiar with in our study of probability, where you roll a die, you end up with a value between 1 and 6. You do a similar thing for a second die, and then inside here we have the sum of those 2 die. So when we're looking at a probability distribution, what are all the different values of the sum of 2 dice that we can have? Well, our smallest one is a value of 2. And what is the probability of getting a 2 when we roll 2 dice? Well, we can see that it happens as one event out of a possible 36. And I want to multiply the value of x times its probability to introduce you to a new concept once I finish the table. So I'm going to do that right now. 2 times 1, 6. I'm just going to leave as 2, 36 right now. Sorry, 2 times 1 over 36 would be 236. We can reduce it. I'm not going to, and you'll see why in a little bit. So what's another possible value we can get when we roll 2 die? Well, we can get 3s. And how many of the events out of 36 would result in a sum of 3? Well, 2 of them would result as a sum of 3. If I do 3 times 2 over 36, I get 6 out of 36. And hopefully you're starting to see a pattern here. I'll do one more with you, and then I'll let you pause the video, you try and fill in the rest, and then check with me. Let's look at 4s as a possible sum of 2 die. That can happen 3 out of 36 times. Multiplying these together gives 12 out of 36. Okay, like I said, you pause and then come back. I'll fill this in quickly, and then you can check your answers with me. Okay, I've gone through all of the different sums that we can have, looked at the probability of getting each sum, and multiplied the value of x times its probability to get this column here. Now, let me ask you this. If you were to roll a pair of dice for a long period of time, what would you expect to be the most common value for sum that would appear? And I think even just seeing from this table, you might expect that 7s would appear most often, right? You have a greater chance of getting a sum of 7 than you do any other sum. I want to introduce you here to something called the expected value. And the expected value is exactly that. It's if you were to do this experiment 100, 1,000, 10,000 times, what would you expect to see as the most common answer? And to find the expected value, which we're going to represent as, in this notation, capital E of x, and we can use capital X because it's the expected value for the sum of two die, which is our variable. What we're going to do is we're going to add up these x times p at x values. And I left them on 36s because we can add them much quicker when they have the same denominator. So adding up all these numerators gives us a value of 252 out of 36. And if you punch that into your calculator, it's not surprising that the most common value of x that you're going to get in this experiment over time would be a 7. So this is a really powerful tool to figure out what the most common answer should be, or what the most common occurrence should be for a particular experiment. Now, if we were to graph this, and there's an image of this in your notes, if we were to graph each of these probability values, and we could convert them to decimals to do so, and I'm just going to do a rough sketch here, you'll notice that we can put the random variable x down here, which is the sum of two die, and we can put all the individual values all the way up to 12. And what's really interesting is that you end up getting something that looks like this. And not surprisingly, the peak is at a value of 7. Okay, because of the beautiful symmetry of this particular experiment. Okay, let's do another example together. This time we're going to change the scenario so that the outcomes are maybe not as symmetrical as our previous example. So this time we're going to do a game. And in this game, a player has to draw a card from a deck of 52 cards. And so if they get an ace, they'll win $30, up $30. If they get a face card, then they win $20. But if they draw any other cards, so I'm going to just call it a 2 to a 10, they will lose $10. And so what we're going to do is do a probability distribution for this, and to see if this is what's defined as a fair game. In other words, do you have a better chance of winning in this game if you played it 100, 1,000, 10,000 times, or do you have a bigger chance of losing, or does it come out neutral? And our probability distribution can help us answer that question. So we're going to let the random variable be equal to the payout, or the amount won or lost. Okay, so this random variable x, capital X, has a set of 3 values it can be. It can either be -10, it can be 20, or it can be 30. Okay, so these are the individual little x values. This is the set of all possible outcomes. So let's do a table. First value for x we can have is 30. We will get that value when we get an ace drawn. And what is the probability of that occurrence happening? Well, how many aces are in the deck? Well, there are 4 out of 52. Okay, so I could write this. I'm going to reduce it down to 1 out of 13, and you'll see why in a little bit. The other scenario we can have is that we could win 20 ducks, and I'm going to put pluses and negatives in front of here just so we don't get it mixed up. And again, we'll get that if we get a face card, so we can be specific. That's a jack, a queen, or a king. And how many face cards are in the deck if we're picking up a random card? Well, there are 12 out of 52 of them. 4 jacks, 4 kings, 4 queens gives a total of 12, which can reduce down to 3 out of 13. And then finally, I will lose $10 if I draw anywhere from a 2 to a 10. How many cards are in the deck? Well, maybe we could do this through subtraction. So 16 of the cards are taken up here. 16 from 52 means there must be 36 other cards remaining. And that can be reduced down to 9 out of 13. So now let's do the value of x times its respective probability. And if we do 30 times 1 over 13, we get 30 out of 13. Don't be alarmed by the fact that's bigger than 1. I'll show you where we're going with this. I can then do 20 times 3 over 13, which is 60 out of 13. And I can do negative 10 times 9, which is negative 90 out of 13. Okay? Now, I'd like to calculate the expected value for this, because the expected value is what's going to tell me if this is a game where I'm more likely to win money or I'm more likely to lose money. Now when I add all these up, you'll see I have 90 out of 13 here, and I take away 90 out of 13. It means I'm left with 0 out of 13, or the expected value is 0. Now this is a good thing, and when we're talking about games, because if it's 0, this is defined as a fair game. So the game is fair. It doesn't favor one side or the other. It's fair when the expected value is 0. Okay. It would be neat to see how a graph of p at x would look versus x. So I'm going to sketch it for you, but you can do a better job in your notes because I've given you some a little mini graph paper thing you can do there. If you count up by 4s, you'll end up getting very close to the top, ending up at 36. And this is your probability for each of those events, p at x. And remember, it's out of 52, okay, or we could do it out of 13 as well. I'm graphing it here out of 52 because I decided to do it that way, but you could also just go up 1, 2, 3, go up to 13 and do it that way as well. The payout, which is our random variable x here, has 3 possible values. It has negative 10, it doesn't have a 0, but it doesn't have a 10, but it does have a 20, and it does have a 30. Whoops, 10 there. So I could graph negative 10 at 9/13. That puts it up, or 9/13 or 36/52s, so 50 seconds. That would put it up here. There's nothing here. Okay, this would be 0 probability, 0 probability. The 20 here, if I'm graphing it out of 52s, we'll go up to 12. So again, if you count by 4s, you'll be able to go about here. And then 4 out of 52 for getting a payout of 30 would be about here. Okay? Now you will notice, again, like I said, these probabilities all add up to 0 when it's a fair game. They all add up to 1 right here. We mentioned that at the beginning of the video, right? There's 9, 12, 13, 13ths. Okay, so all these add up to 1. And the graph would look something like this. Okay. Now, there's an interesting scenario if you try to do a probability distribution for something where the probability is always identical. And I want to take a moment just to address that before we finish. So let's say that you allow your random variable just to be rolling a single die. So in that case, your random variable has 6 possible values: a 1, a 2, a 3, a 4, a 5, or a 6. And if you were to plot the probability of getting a 1, or a 2, or a 3, or a 4, or a 5, or a 6, well, what is the probability of getting a 1 when you roll a die? It would be a 6th. I'm going to put 1/6 up here. What's your probability for rolling a 2? Also a 6th. How about a 3? And you start to notice that the line for this becomes straight. This is called a uniform distribution. And a uniform distribution is a very, very simple distribution where all of the probabilities for each of the events is identical and it results in a completely straight line. Can you think of other scenarios where this would also be the case? Think about if you flip a coin. You're either going to get a heads or a tails, right? Maybe you let heads have a value of 1 and you let tails have a value of 2, and it's 50-50. Would also be a uniform distribution. What about if you pick a number randomly from 1 to 100, or from 0 to 100, right? You have a 1/100th chance for each of those. Again, a uniform distribution. Okay, and so there aren't as many scenarios in real life that follow uniform distributions, but they're the nicest, easiest ones to start with. And that's what we will start with in this lesson. All right, enjoy the practice, and we'll teach you about the next type of distribution for discrete variables called binomial distribution in the next lesson.